to end our chapter, what we really want to focus on now is Le Chatelier. What happens if equilibrium is disturbed? What happens is once we reach an equilibrium, we can still mess with it and change it, and we can add things and take things away. And so what Le Chatelier tells us is, how is stress on the equilibrium, disturbing the equilibrium, affecting the overall concentration values? What happens to the shift of equilibrium? How is equilibrium restored? Because the driving force of an equilibrium equation is to reach equilibrium and stay there. If conditions are changed in an equilibrium, such as the concentrations of the chemicals, then the change will, it will spark a change in those concentrations until equilibrium is reestablished. So Le Chatelier's principle guides us in predicting the effects of various changes in the conditions of the position of equilibrium. It says that if a system at equilibrium is disturbed, the position of the equilibrium will shift to minimize that disturbance. Disturbances all involve making the system open. So open to the environment, adding more reactant, adding more product, removing product, changing the temperature, etc. Now, disturbing the equilibrium can be by adding reactants, all right? It can be by removing reactants, and it can be by changing temperature. Now, adding reactants will decrease the amount of the other reactants, right? And increase the amount of products. If we're increasing a reactant, we're really saying that we're adding more of our reactant, and the reactants are stressed. There's too many. And as long as that reactant is added, it will drive the reaction forward. The reaction proceeds right to the product side. Now, at the new equilibrium for adding a reactant, it will be found that the equilibrium constant is the same. It's like a magic trick. K will be the same. For removing product, we think removing something from the product side, the reaction's going to proceed to the right. Again, changing the amounts, whether adding or subtracting, is going to shift the equilibrium to fill the void. Now, equilibrium shifts away from the side with added chemicals or towards the side of removed chemicals. This is the overall statement we want to focus on. If you add something, the reaction will go opposite of that side that the chemical was added. If you remove something, the reaction will proceed to fill that void. And remember, adding a solid or a pure liquid is not going to change any concentration. Therefore, since it's not written in the K, our equilibrium expression, it's not going to affect our equilibrium. The only things that are affected by Le Chatelier's principle in terms of changing concentration is gases or aqueous things. What we see here in this reaction is that if we add more product, NO2, put that in the reaction flask, the equilibrium is disturbed. And so we shift to the opposite side. We add something, we want to use it. In this case, we add a product, we shift backwards to the reactant so that we can use the product that we just added. Graphical representations, I think, are super helpful. Equilibrium is established right here in this yellow, right? Q is equal to K. If we add something, like say NO, a product, the equilibrium is going to shift to start decreasing the amount of that product, increasing the amount of reactant, until again, we restore equilibrium and Q is equal to K. Opposite goes for if we were to add a reactant. We see equilibrium is established here, Q is equal to K. We add N2O4, we add the reactant. it causes that equilibrium to shift and decrease the amount of reactant that we added. We can increase the amount of product we added reactant, so let's make more. And then equilibrium is established again. Now, adding gases. Again, concentration is a little bit easier. When we think about molarity, all we have to add is more moles of something. Now, adding a gaseous reactant, if we have gases in our reaction, we think about adding gases, meaning increasing the partial pressure. Anytime we add a reactant this way, we cause the equilibrium to shift to the product side. We're going to use that reactant. Increasing the partial pressure increases its concentration. It does not increase the partial pressure of the other gases in the mixture. So we need to make sure that when we're increasing, again, a partial pressure, this way, if we're adding a gaseous reactant, it's increasing the partial pressure of whatever gaseous reactant or product we decide to add. Adding an inert gas, something that's not in the reaction itself, has no effect on the position of the equilibrium. Again, if it's not in the rate law, if it's not in the equilibrium concentration, then it's not going to affect anything. What could affect us, though, is a volume change on gases. Volume changes for gases does increase their or decrease their partial pressure. If you decrease the volume, you are putting those gases closer together. This is increasing their partial pressure. It does not change the concentration of solutions. If you have solutions in gases, you got to think about them separately. If the partial pressure of the gases increase, then the total pressure of the container will increase. And according to Le Chatelier, the equilibrium should shift to remove the pressure. So this is not increasing the partial pressure of one specific chemical. Decreasing or increasing the volume changes all of the partial pressures. And so what happens is we actually see a shift based off of the overall balanced equation. The way the system reduces pressure, if we increase or decrease the volume, decreasing the volume, increase the pressure, we want to reduce the number of gas molecules in the container. So when the volume decreases, the equilibrium will shift to the side with fewer gas particles. The same thing happens on the opposite end. If we increase the volume, we're decreasing the partial pressure. We're essentially saying, hey, you have more room. The equilibrium will shift to the side with more gas particles. Here's that effect. We have this reaction N2 and 3H2 yields 2 NH3 molecules. Now, when we increase the pressure by decreasing the volume, we proceed to the side with less particles. That happens to be the products. There's only 2 gas particles versus 3 + 1, 4 gas particles on the reactant side. So if we decrease the volume or increase the overall pressure of this system, the reaction is going to shift to the product to the right. Opposite, increase volume or decrease the pressure, the reaction is going to proceed to the side with more gas particles, which happens to be the reactant side in this equation. Temperature has an interesting effect on our equilibrium and the K value. This is the only time that the K value would actually change. Changing pressure, changing concentration, we're not really changing as much our K value when we're instituting a new reactant or a new product. But adding heat to an exothermic reaction will always change the concentrations of the products and the concentrations of the reactants, and then therefore change the actual value of K. In an exothermic reaction, remember that heat is released. Heat is acting as a product. There it is on the product side for an exothermic reaction. So adding heat add something on the product side, the equilibrium will shift to the reactant side, which means we will be decreasing K. We will make less products, we will make more reactants, and therefore the denominator will get bigger. The exact opposite for an endothermic reaction. Endothermic heat is acting as a reactant. Heat is required for those reactions. So when heat is behaving like a reactant, increasing the temperature is like adding heat, and therefore Le Chatelier's principle will say you are adding a reactant, you drive that reaction to the right, to the product side. This then makes more products and therefore increases the numerator of our K value and increases K. Summary overall for that effect of changes in temperature. In an exothermic chemical reaction, heat is a product. Increasing the temperature shifts the reaction to the left, to the reactant side. Decreasing the temperature of an exothermic reaction is like removing a product. It shifts the equilibrium to the right, to the products. For an endothermic reaction, heat is a reactant. Increasing that reactant of heat means that the reaction will proceed to the right, make more products. Decreasing the temperature of an endothermic reaction shifts the reaction to the left, puts that direction towards the reactants. What I highly recommend involving heat, whether it's exothermic or endothermic, pop it in the balanced chemical equation as either the reactant or the product, and therefore treat it as such. Now, the last thing that I want to go over is just briefly the idea of a catalyst. We talked about catalysts in terms of the rate of the reaction, right? Catalysts decrease the rate or increase the rate of the reaction. They're decreasing the activation energy. Catalysts provide an alternative or more efficient mechanism. Catalysts work for both forward and reverse reactions, though. So a catalyst affects the rate of the forward and the reverse reactions by the same factor. Therefore, overall, catalysts do not affect equilibrium at all. Nice.